Welcome and good afternoon from my side also. You are very welcome today to join me in a small tour around the new development we have done for you, a new surface velocity radar, which is a huge, amazing instrument to get contact-free, reliable and maintenance-free measurements of the water surface velocity. This is the agenda I want to cross with you today. First, I think we talk a little bit about the motivation. Why do we measure surface velocity? What is the reason behind? Why it is so important today, even this time? So we see a huge trend everywhere in the world to go to contactless measurements to get velocity information from the river in open channels. Next is the measuring principle. What is behind? How does it work? And what are the technical data of this sensor? What are the limitations of this instrument? Because every instrument, every sensor has limitations due to physics, due to environmental conditions, and further. We will talk a little bit about the measurement data. This is what comes out, what you can use finally. Of course, velocity data, and how you can be sure that data have a good quality. So we also will have quality discussions. We have provided metadata for you. You will see this later on. We talk about system components and configuration if you want to have a total complete system to get discharge in the field, because the SVR 100, and this is the first remark I make at this point, is just the velocity sensor. It's not a complete system. It's just a sensor which you can connect to your system, to your data logger, in order to compute finally discharge with assistance, of course, of water level measurements. And we talk about the site reconnaissance, installation, operation aspects, and calibration, because each continuous operating system needs to be calibrated in the end. Finally, not to forget, scope of delivery. What will you keep in your hand if you have an order placed for this instrument? Okay, let's start with the motivation. Why do we measure surface velocities? That's pretty easy to answer. The surface velocity measurement is one of the oldest methods in hydrometry. So even long time before we had any mechanical type meter available, hydrologists have done surface velocity measurements. So what you need is just a tree-pit surface with a flag on it. You need a good straight length of the river. You need maybe a tape to define the length of, for example, in this case, 50 meters. Everybody has today a smartphone in his pocket. You can take the stopwatch, you can measure the time, you have the length, and you divide the length by the time, and you know exactly it's 1.66 meters per second for this surface velocity of this river. Very easy to do in the field. And even long time before mechanical meter, I told you we have done this with floaters, just like tree pit surfaces, or we took hollow bowls which were swimming on the water surface, or the people took locks with a line, with a strip on it, where they have knots inside which you can count. Or they took, for example, something like an undershot mill wheel where it is rotating, and even here the strip which is on it has knots. You can count the knots in a certain time. You know exactly the velocity at this point. It's an old traditional method. What you can do also today is you take a lemon, for example. You go out in the field and put the lemon in the water. Then you discover how it's floating away. If you have a strength, if you have a watch, you can count the time, and then you know the velocity of the surface of this river. If you want to be sustainable, of course, you can take a landing net and pick them up later on and do it a second time. It's up to you. Why do we measure surface velocity? The international standard, the ISO 748, which is hydrometry measurement of liquid flow in open channels using current meters or floats, this contains also a method. It's called the one-point surface velocity method. And for this, you know, if you have a flood situation, you need to be very fast. You have unsteady flow in the field. You need to make quick measurements. Then it's okay if you do the surface point of each vertical. And if you take the surface velocity and you multiplicate it with a correction factor, you will get the mean velocity in this vertical. So in similar procedure you can do with your surface velocity radar. You measure on the water surface, you take a correction factor to get the average velocity. So that these methods are well known, and OTT itself has a long experience in mechanical and also in electronic meters, flow meters. And finally, to summarize this, Why do we measure surface velocity? It is because it's one of the oldest measuring methods in hydrometry, well tried, easy operability with the aid of floaters, clock, or graduate tapes. It is indexing the mean channel velocity if site reconnaissance has been done expert and hydraulics on site are well defined. It is safe since it's contactless, so you don't need to enter the water, you don't need to install anything in the water, you are out of the water, you look from the top at the water surface. And it's a suitable method for continuous flow monitoring in all flow situations, particularly during floods, of course, when floating debris passes the site, and high sediment load will be a challenge for submerged instruments. From the historical review, maybe one or other of you may remember the old Calesto V. Calesto V was a surface velocity radar we provided for a couple of years from 2000 up to 2012. The velocity range was a little bit limited, was 0.5 up to 4 meters per second. The dimension was big, so you see this in the picture here, a huge tube with a weight of 8 kilograms. This is heavy, and even if you want to install it in the field or you are below a bridge and you need to do this, it was a heavy work. Today, what we have now is the OTT SVR 100 since May this year, and the velocity range is much more expensive. So it's 0.0, it's 8 centimeters per second up to 15 meters per second. The dimension is very small, it's smart, it fits in the palm of your hand, and the weight is just 820 grams without the swivel mount, and if it is mount, it's 1.5, it's also not much. So there's a huge difference between both, and you see the development is going ahead. How does the sensor work? This is not difficult, it's easy. It's a Doppler sensor. The SVR 100 is a radar sensor. We are operating with electromagnetic waves. So we orient the sensor parallel to the main flow direction. We tilt it against the water surface by an angle of recommended 30 degrees. And then it's transmitting and receiving electromagnetic waves. The returning echoes provide a shift in frequency, respectively in wavelength. This is the so-called Doppler effect. A lot of you will know this from acoustic instruments, ADCPs, and so on. They also use Doppler effect with acoustic transducers. From this, the weight of the water surface then can be derived. And this is the easiest principle. You see, look to the water surface, transmit and receive electromagnetic waves, and take the Doppler shift and get the velocity from it. Same here, you can mount it on a bridge somewhere. Then you will have a footprint on the water surface because the area is an elliptical area where you get the reflections from. Depending on the height of the sensor and the distance, the area will change in size, of course. Technical data, very important. What can we expect? So the velocity range is very wide. So 0.0 meter per second up to 15 meter per second with a resolution of 0.1 millimeter per second. The accuracy, plus minus % of the measured value. So you will think, oh, that's good. How do they guarantee us this? We have been with the sensor in a laboratory in Switzerland, which is METAS, the biggest and I think also the oldest laboratory for hydrometric calibrations we have here in Europe. And we got a certificate for it. So they took the instrument to the carriage and the rating tank, the tow tank, and they did several tests with different velocities, starting with the 0.08 up to 2 meters per second. And for each carriage pure, the accuracy was confirmed to be less than 2% of the measured value. This was a very great result. We are very proud of it and can provide you a certificate if you want. We have serial interface on board. That means we have an RS-232 interface and we have an RS-485 interface. And we can run 2 different communication protocols. We can send SDI commands via RS-485, and we can communicate via Modbus RTU. Power supply is a wide range between 9 and 27. Just an additional remark to this. So the serial interface is, as you see here, RS-232 and RS-485. We don't have a physical SDI-12 interface. That means we can't take the sensor, or we can't wake him up and say, okay, start your measurement, give me the values back, and then go into sleep mode. This is not possible here. If we power the instrument, it is powered on. then it's continuously operating. You can send SDI command via RS-485 and request data and change parameters, but it is not a physical SDI-12 interface where you have the power supply included. Technical data in an overview here, we talked about already about distance. Distance to the detection distance is 1 to 50 meters, so which is the length of the radar beam finally. The distance to the water from the installation point, the water surface, vertical is the minimum 0.5 meter up to 25 meters. We are operating in a radar frequency band 24 gigahertz K-band. We have this 2 serial interfaces. We have protocols, SDI and Modbus, and the power supply. We have this nice, really nice mounting swivel mount, which gives you all the directions in order to get a good installation in the field. And the housing is IP68, which means that it may rain, it's made all be dive. So if the sensor goes below water for a certain period of time, it should not happen anything. Measurement data. What can we expect to get from the instrument? Of course, first, which is the most important is velocity. So we will get instantaneous velocities, and we get average velocity. And if you want to compute discharge and you don't want to have this big up and down on the water surface, or the turbulence and so on, if you want to have a good value average, then you will take the average velocity of the output stream. And each velocity comes along with additional metadata information. That means each velocity will provide also in the same record the tilt angle, that you know exactly is the instrument still aligned in the right angle. You will get the flow direction. Is the flow coming, is it upstream or downstream? So is it coming direct into the sensor, or is it going away from the sensor? You will get an index of signal quality. That means QoS is the signal strength index. So you have an index from 0, 1, 2, and 3. And you get also a vibration index, because if the sensor is starting to vibrate, this affects also the accuracy of measured velocities, because it has an effect of the shift. You see here in this line different time and the command send from the SDI command, average velocity, instantaneous value, pitch roll, and the both signal strength and sensor vibration index values. Vibration sensor. The integrated vibration sensor detects sensor vibrations. It reports an index. That means 0 is no vibration. 1 is a little bit, so all the measured values with 1 may be accepted also, because just a low influence. 2 is strong vibration, and 3 is very strong vibration. So if you have index 2 and 3, I would like to recommend to discard the values. Tilt sensor is integrated also to provide the user the information about the sensor position, if the sensor position has changed, because the tilt, the angle, is part of the computation of the velocity on the surface by cosine function. The sensor position has a direct influence on the measurement, so it's very important to know if something has changed on site due to vandalism, due to very strong wind gradients, whatever happens in the field. And this data is also available via SDI-12 with each measurement as intonation value in degree. We have measurement data filter algorithms. So wind, waves, vibration, precipitation, they can introduce spikes or noise in the measurement data. And if those events do not represent the real measured velocities, a filter can be applied directly in the sensor using an SDI command. So the filter length can be defined by you. And as you see here in the small movie, it was a day where we had very, very heavy rainfall here in the surrounding of Berlin. We have been measuring. The tripod was keeping the sensor. It was just a test in the field, and it worked perfect. Or another is, for another example, if you have wind going against the flow direction. So the main flow direction is the blue arrow here. The river is moving so forward. And then wind comes and drifts the surface back on one side of the river. If the instrument is directly looking at this area and you have defined you accept only flow which is outgoing, then the wind effect will be negliged, so it will be compensated. You will not see any erroneous measurements. That means we have a direction filter on board which prevents the radar from measuring waves that are heading in the wrong direction. You can activate this and deactivate this with an SDI12 command also. The signal quality as an index provides you the information whether you have good signals, and 1 up to 3 are bad signals. The readings should be discarded if you have 1 up to 3. Most of the time you see 0, hopefully, but if you have a 1 or 2 or 3, then you can decide what to do with your data. I would like that you discard it. What system components are required to get a discharge finally? Of course, first you need the SVR100 for measuring the surface velocity. Then you will need a level sensor because you need the cross-sectional area. You know, discharge is area times average velocity in the section, and for getting the area, you need a level measurement. You will need a data logger to compute the discharge. It could be a NetDL, it can also be a Sutlink, Sutron, so any data logger which is able to manage tables inside and has an RS485 interface can be used. And of course, you will need a housing with power supply, and okay, the power supply is solar. If you have a solar powered station, please keep in mind the SVR100 is continuous operating. So in this case, you have a solar panel, then it's recommended to switch it on and off with a relay. So you can't use an SDI command, you need to switch it on physically with a relay in order to save energy. The system components and configuration in a brief overview now. So some use cases. On one side, you have above the border surface velocity radar, and you have a level sensor. Then you can use the NetDL. The NetDL is triggering the measurements, calculating discharge. It's alarm based on measurements and metadata, so you can be informed if anything happens in the field. Hardware interfaces between sensor and PC, and you can power the sensor also from the NetDL. Then you have a USB connection to SDI12 interface software, and with this software we can go through the NetDL. You can set filters, can change the sender address, you can retrieve measured data, you can make a graph, and so on and so on. You show graphs and tables and all these things. This is one use case. The other one is if you take one of the loggers from Sutron, Sutlink, for example, Sutlink 3. Here you have a Wi-Fi connection between the PC and the Sutlink logger. You can also here set sensor address, set filters, show graphs, and on the logger itself, the discharge will be computed finally. If you want to just communicate with the SVR100, you can take the USB SDI12 interface we provide. This is a small gray box here in the picture, and you take the SDI12 interface software, and then you can connect via the small box to the sensor. You can do settings, you can set filters, you can check anything of the instrument, and you can also start continuous measurements, single measurements, and show graphs and tables. This is possible if you just want to communicate with the sensor. Here's a small screenshot from this SDI12 interface software. You see this is the real measurement mode. You can switch on and off different parameters here, for example, pitch and flow direction, signal strength indicator, and vibration indicator is off, but here is just on the average velocity and the instantaneous velocity. You can connect to the sensor as well with RS232 interface. Then you will need to have a separate cable and external power supply. So you need an RS232 connector and external power supply. And with the SVR100 operating software, which we will make available for you for download, you will be able, for example, to upgrade the firmware on the sensor itself. This is only possible with this operating software. And you will also be able to change the communication protocol between SDI12 over RS485 and Modbus RTU. But if your customer, you already know what type of communication is required in the field, then you can select the right order number, and we can distinguish between. And we have a factory preset communication protocol for you, so there's no need to take this software and to change it afterwards. This is the screenshot of the operating software. You see a very, very nice overview. See, we can set the average filter type, filter length, and flow direction filter on, off both directions, and the RS485 protocol between SDI12 and Modbus RTU. Now we talk a little bit about the site reconnaissance. That means site reconnaissance starts always in the office. So you may use topographic and geologic maps or aerial pictures, satellite images, to get a better overview of the territory where the measuring site shall be set up. So on the right side, we have OpenStreetMap, for example, which gives you good mapping material. Look for a straight reach of the stream. That's very important, where the flow is parallel to the banks. And mark potential sites on the map. So in this case here on the right side, we have a bridge, which is really crossing more or less a right angle, the river which is flowing straight. The rule of thumb is the water is flowing parallel to the banks if the water course is straight over a distance of 5 to 10 times the channel width. And the recommendation is also that the straight length upstream should be at least twice that downstream. This rule comes also from side-looking instruments where you also need the straight length. So 2 times upstream and 1 time down, that's the straight length required. Site reconnaissance starts in the office. If available, you can take a look at existing discharge measurement records from your selected site. So if you have a database where you store all the mechanical type meter measurements, ADCP measurements, magnetic inductive probes, dilution method, whatever, if you have such an overview, such a database, then you can check for your site what is the relationship between the mean channel velocity and the maximum surface velocity. And if you see, if you take both and you make a regression with, for example, Excel, and you see a good regression coefficient, in this case here 0.992, which is pretty good, then you can be sure that the measurement of the surface velocity is absolutely sufficiently to get a reliable and accurate discharge value for any stage you have in the field. Site reconnaissance continues then in the field, so you can apply portable flow meters, just like ADCP or mechanical meter, whatever, to determine the position vertical of the maximum in-stream, respectively the maximum surface velocity, as well as the velocity distribution across the river. So you, for example, with ADCPs, you have this magnitude plot where you see in colors where's the maximum velocity in my cross-section. You can conduct cross-section surveys to set up a stage area rating because you need the cross-section finally always for discharge computation. And good sites, they provide always a stable position of the maximum surface velocity, even if hydraulic conditions on site vary. This is very important. And from this we have developed the top three criteria for good sites. So first, I'm repeating this, you need a straight channel or river which is parallel, parallel streamlines, free of growing weeds, channel obstructions, rocks, and also free of macro turbulences. The second, you need uniform shaped cross sections. That means either rectangular, trapezoidal, parabolic, something like this, with a stable riverbed and banks, regular velocity distributions, and a stable position of the maximum surface velocity. And, of course, you want to have reflections from the water surface in order to get a Doppler shift. You need a rough water surface. And we have very, very good and high sophisticated internal electronics, so that means we just need around minimum 1 millimeter wave height on the water surface. We have done test measurements with very smooth water surfaces, and we got very good results. So you need at least 1 millimeter wave height on the water surface, even if it's not really visible for your eye. But if there's a wave on the surface, we will get reflections, we get power back to the radar, and then it works. That's why the start velocity 0.0 meter per second is very small, but it has proven to be correct. And it's also recommended to have minimized influence of wind gradients in the field. Wind is, you can imagine, a challenge, of course, for radar. Not wind which is going in direction or against the flow. That depends on the strength of the wind. Of course, you can compensate it most of the time with the averaging time, but wind which is coming from the side and has a strong gradient, and this is creating then finally cross flow, and then it makes no sense anymore to measure with the surface velocity radar. Some examples how to select a good site. So what we see on the left, this is a small 5-meter wide river here in Berlin, just not that deep. The depth depends between 30 centimeter and 1 meter max. And you see it's flowing very, very with a smooth surface. It's sometimes very slow, sometimes goes down to 10 centimeters per second and up to 1 meter and 20 per second. This is good. It's a regular profile, and the waves on the surface are sufficient. On the right side, we see the Salzach river in Austria, in Salzburg, which is a little bit more, it's much more bigger, you see, okay. More power, so you see the waves are totally different from the left example. You have big waves, and here, of course, you can measure with the instrument pretty good. Another example, which is not so good, on the left side, we see a bridge which is crossing two outlets of a river basin on the left side. This is at the Philippines, in Manila, the capital of the Philippines. This is the water supplying company of Manila, or one of the water supplying companies. And in the reservoir of the left side, you see the guy who is standing on the bridge is taking his stick and putting the plants in these two outlets below. They have a diameter of more than 1 meter. And the plants is lotus blossoms. They need to clean the reservoir because they need the quality of the water for drinking water. And all the blossoms go down in the other reservoir on the right side. And what I want to show you is how it looks like if just a moment, if the reservoir stop here, start. You see this big waves here and the foam and all these things. So this is macro turbulence. In this area, you will not be successful with surface velocity radars. This will never work. So surface like this, absolutely no chance. You see all the blossoms, which then will be picked up in the evening by a truck. On the right side, this is a station or it is a bridge in downtown of Berlin, where I live. So those of you who have been in Berlin, maybe they have seen this. So this bridge is of metal. Sorry, I need to go back, start it again. There's a lot of traffic crossing the bridge. You see there's a public train. Every 2 minutes is one train going in the one direction and then also in the other direction. And there are more lines in the back where we have ICE trains and all these things. So that means we have always vibrations on this structure, not visible for your eyes, but measurable for any vibrations. And that means if you have a bridge like this, where you have a lot of traffic on it, you will need to take a deeper look at it, and it probably takes a little bit more time to make a good site evaluation. Yeah, that's important. Another example is from Bavaria. It's in the mountains now. Here, same example. In this area where you have this big microturbulence, there's no chance to measure. But here, more closer to the bridge, it will be possible. So there, no chance, but here, of course, that's fine. And on the right side, also in the Alps, a small river close to Kempten, to our facility in Kempten. This was a day where they had low water situation in it, so just a few centimeter water level, and the velocity was 0.3 meter per second. And we have compared this with measurement of mechanic type, with magnetic inductive probe, MF Pro, and the velocity was still the same. So some other examples without moving now. So if you have, for example, an inlet or from the side, or side flow is coming here at a certain point, it makes no sense to measure here because the index velocity ratio will be disturbed by cross flow from the side. If you have a bridge with big pillars inside, it doesn't make sense to measure downstream because you have all these foam, you have high turbulence zones here. If it is not, if you have no other chance, you need to point upstream then. But also here, be careful and take a good site survey in advance. Where can you install the sensor? Of course, mostly you will take a bridge. So either you take the railway of a bridge, you put it here on the side, or you go below a bridge. If that is possible, that's more recommended because then you can hide your cable in a protection tube below the bridge, and it's also protected from vandalism, and it is also protected if strong rain is falling, so the first 2-3 meters are not affected by rain. That is pretty good. Anyway, rain is not an issue because rain goes away from the transducer. It's creating a negative Doppler shift, and if you have defined only the positive shift is accepted, then means, and you point upstream, then you will only see the velocity created by the flow itself, and rain will not be reported. Or you take a jib, like in the picture here on the right side. This was our first station we have installed in Germany in August this year, where the Water Environmental Authority of Rosenheim, they created this jib here. At the end, they have mounted a radar level sensor for level measurement and the surface velocity radar for the flow measurement for the velocity. And both values are recorded in NetDL, and the computation of discharge is also done in the NetDL finally. Yeah, that's the question, how we get discharge in the end, from velocity to discharge. Again, for discharge, Q, you will need the mean velocity in your cross-section, and you will need the cross-sectional area itself. We don't measure the mean velocity directly. What we do is we measure the surface velocity, which is bigger than the mean velocity, of course. The surface velocity measured by the SVR 100. So that means we need to correct the surface velocity. We need to multiply it with a correction factor, calibration factor. And the question is, where does it come from? And for this, we have a software developed, which is ProDis 2. Both of you who are already running SLD, they know ProDis 2, because we also do calibrations for the side-looking Doppler. And we have also a function inside to calibrate surface velocity measurements with the SVR 100. Q is average velocity times section, and we need the K factor coming out of ProDis 2. The ProDis is a simple, clear, and chronological management of site system calibration data. You can compute velocity index ratings with this software. You can also apply theoretical models for getting the K values. We have a simplified step-by-step user guidance on it for all calibration steps. We have different input interfaces for example, for your cross-sectional data. So the elevation of the bottom of your river and the distance to the point. And a clear and comprehensive calibration report is output finally also in the end. So just like some screenshots, show you some screenshots from ProDis. This is the management of the cross-section. So you see a table here which manages the distance to the reference point at the bank and the height, the elevation, of course, of your river. And so we can, for each point you see here in this graph, we have here a pair of values in the table. You can enter this manually by hand. You can also import an Excel sheet from Excel where all the data already are in. So then you assign a date from when it's valid. You enter the height reference. Is it a meter above datum, or is it meter above the bottom of the channel, whatever. And you need to define the values from minimum to maximum, so the range for which you want to have calibration factors be computed finally. In the next step, you will need to manage the measuring system, in this case an SVR 100. So you need to talk to the system. This is the distance from the reference point on the bank. So at 2.3 meter, I have mounted my SVR 100, which is 3 meters above the bottom here. And the angle, the tilt angle, 30 degrees. So we know exactly which area is covered by the footprint, and then we can compute with the theoretical model the calibration values. We have 3 types of calibrations inside. Theoretical profiles means we assume that at each point of the section we have a logarithmic distribution of the velocity. If you take the measured velocity profiles, then you can take, for example, measurements done with an MF Pro or with a mechanical type meter. Then you know the real existing velocity distribution on site. And if you do a velocity index method, it's where the point is right now here, then you just feed the system, the ProDis 2 software, with your results from your hydrometric calibration measurements on site. So you go to the field at different flow situations, you do a comparing measurement, you enter into ProDis the date and the start time of your measurement and the stop time, and the result, what you have measured, the Q, cubic meter per second, and the water level. And you enter also the sensor data from the SVR 100 for the same time period. And what ProDis is doing in the back, this is the index method. It's computing the real existing mean velocity of the section from your comparing measurement and compares this or relates this to the velocity of the surface velocity radar. If you have done this for different water level situations, you will get a regression. If the regression function is fine and the coefficient is more above 0.9, then you have a very good relationship, and you can take this velocity index ratio for computing your discharges. The output is finally a table where you have the stage, you have your area, you have your K value, and the product of both stage and K.A goes into the logger in order to compute finally discharges with the velocity measured by the surface velocity radar. And also a nice calibration report is available as a PDF file. So for documentation, for handed over to other people who are interested in, and for reporting to, I don't know, to whom it may concern. Yeah, what is the scope of delivery? So we are finally approaching the end of the presentation. Scope of delivery is, of course, the sensor. That's very important. You want to have a sensor. It's the SVR 100 together with the swivel mount. You see also that we have a graduated scaling here on the side, which makes it easier for you to orient the sensor if you are below a bridge. And of course, you will see the tilt angle also in the software. But for those who are below and taking tools and screw and so on and have to fix it, they want to see in the field what is the angle. And that's why we have a graduated scaling on the side. You will get 10-meter cable. On one side is a plug. On the other side is open end. And you will get a multilingual short instruction. It's just a few sites with how to take it, how to install it. But that's it. And of course, a packaging where everything's inside. What you don't get, and which is not included, are the screws for wall mount. So if you want to have screws, you will need 4 screws here to take to fix the swivel mount. What is not included is wrench. Extended manual is not included, but we are working on an extended manual with a lot of information around the sensor, with recommendations for site selection, for troubleshooting, and so on and so on. This is nearly at 90% at the moment, so if it is ready, it will be available for download from our homepage. And what also is not included is an RS-232 converter and adapter, which is required if you want to communicate with the sensor via the OTT SVR 100 user software. And if you want to, for example, make an upgrade of the instrument with a new firmware. It's not our target to have always every month a new firmware for you. No, don't fear this. But if it is required at some time and you want to communicate and upgrade by yourself, you will need this converter. We have this in the price list, so no problem. And we have also longer cables in the price list. So we have 2 variants. 10 meter is standard. We can also get 50 meter. And as I told you already in the beginning, if you know you want to have Modbus, you can tell us this with your order, and then we can make it preset, factory preset for you that it's already Modbus communicating if you receive it. Why discharge measurement by SVR 100? This is the last page. Discharge data, you will have discharge data around the clock. So every day, every minute, so it depends on your, of course, and your time intervals, but you have always discharge data available. Even if a flood is coming in, for example, your mobile devices will be affected by floating debris you can't measure with ADCP because it's too turbulent and too much air in the water, whatever. Here you will have discharge data all the time. You will get metadata for quality assurance and quality control, just like the tilt angle, vibration index, and an index for the signal quality. You will get you can measure floods and other extreme events, even also low water situations. It's a simple installation. There is no underwater installation required, so you don't need a diver as, for example, for side-looking Doppler or travel time systems. Everything is outside of the water. There's an automatic detection of the flow direction. There's maintenance free, so there is nothing to maintain on the sensor, except maybe there are some spiders climbing inside, so okay, but spider, they don't affect your measurement. And there's a minimum surface roughness required, just 1 millimeter, as I told you. And it is suitable for upgrading existing gauging stations. So if you have already water level measurement stations in the field with all the periphery around, with all the logistics, then you just add a surface velocity sensor and you can make this a discharge station. And which we are very proud of is we have a certified by METAS concerning measurement accuracy. So there's a certification which proves that this instrument is really measuring accurate. So far, so good. This was a brief introduction into this new surface velocity radar. I thank you for listening and for participating this day here in the afternoon. For some of you, maybe it's early in the morning or late in the night, I don't know. I hope it was a little bit interesting for you, and we are very pleased to answer your questions. So if you may have any question, you can ask me now, or you can also write an email, whatever, and you will get a written answer within the next days. Thank you.